Now it's time to look at this mysterious data structure that stores the order of the line segments along the sweep line. If you go over the code that we've seen in the previous slide, we need this following operations from this data structure. We need this data structure to maintain an order. In other words, if you have this set of line segments intersecting it, this one should be the first, second, third, and 4 and 5. We need to be able to find operation to do some kind of a search operation, right? So given a new line segment, right? So this is a new line segment that I add to the picture. I need to find the previous and the next line segments on the sweep line that come before and after this new line segment. This data also needs to be dynamic. I should be able to insert a new line segment. For example, this new line segment will be inserted, and now it will be, I guess, segment number 3. So then this will be 3, this will be 4, 5, and 6. And I also need to be able to do delete. And finally, I also need to be able to do swap order. The swap order can obviously be supported using insert and delete, because, you know, if you have I and I plus 1, you can think of this swap operation as you delete I and you delete I plus 1, then you insert them in the So this swap order operation is not essentially something new. We can simulate using insert and delete. But now the question is, how does this work, right? Because these are line segments. How do we maintain this data structure, or is it complicated? If you want, you can pause this video to think about this for a moment. Because in fact, it's a very cool idea that we can implement this without actually coming up with a new data structure. Just think about that for a minute before continuing. The solution is actually very surprising, and it's very simple. The solution is that any search data structure, any dynamic binary search tree can do this. For example, you can use a red-black tree. And if you pick, let's say, the correct programming language, you might not need to do pretty much anything. Let me explain what do I mean by that. So what is a binary search tree? A binary search tree is a search structure on elements that can be compared. People wrongly assume that a binary search tree is a data structure that works on numbers. But that's not true at all. You don't need numbers to use a binary search tree, because the only operation that you need in a search tree is a comparison operation. And to be able to compare two things, you don't need to have those things be numbers. If you work with, let's say, object-oriented programming languages, you know that you can compare objects. Or if you've worked with C++, you know that you can overload the comparison operation and you can compare any objects or anything to anything essentially. And that's what we need to implement this data structure. We want these segments to be ordered, so we need to have a way to compare them. And now that's the question. How can we compare two line segments? In general, that is not possible, right? Because if you have a line segment like this and you have a line segment like this, which one is to the left of which one? In this case, you could maybe say that this is to the left of this line segment, but if they go like this, you have two line segments that go like this, which one is to the left of the other one? The answer is not clear. It's actually quite ambiguous. But in this problem, we have a sweep line. We don't want to compare any two arbitrary line segments. We want to compare two line segments that intersect the sweep line. And once I add the sweep line, then the comparison is meaningful. I have the leftmost line segment, I have the rightmost line segment, and two line segments can be compared. So the only question here is that how do we code something like this? And the answer is, again, relatively simple. You can compare them by calculating their intersection points with the sweep line, and essentially work something like this. We say a line segment is smaller than another line segment Again, think of it as you're overloading this comparison operation in, let's say, your C++, or you're providing a comparator operation for whatever library that you use in your programming language that can compare objects. We say S1 is smaller than S2 if the intersection of S1 and L is to the left of intersection of S2 and L. So in this picture, that's the intersection of, say, the first segment. This is the intersection point of the second segment with the sweep line. When I compare this x coordinates, I can easily see that this x coordinate is less than this other x coordinate. This comparison requires calculating the intersection point, and to be able to calculate the intersection points, I need the y coordinate of the sweep line. But as we discussed, this y coordinate continuously changes. But here's the observation: even though this y coordinate is continuously changes, this does not change the result of this operation, because as long as nothing is changing in the picture, even if I slide the sweep line slightly below, the result of the comparison won't change. This x coordinate is still smaller than that x coordinate. So it is sufficient to do this comparison or this computation of intersection points at the event points. And also, this is also another reason why when we get to the intersection points, we need to swap their order, because suddenly at this point in time, the order along the sweep line will change. So we need to essentially swap their ordering, because at this point in time, the result of the comparison changes. Before this, S1 was smaller than S2. After this point, S2 will be smaller than S1. Okay. And essentially, this comparison is the only operation that we need to implement, and just use a generic dynamic binary search tree data structure to implement the sweep line. And that essentially concludes the description of the sweep line algorithm.